the stack dynamically allocated part of data memory. This is where the stack frames go, but that's not what I'm referring to when I'm talking about push and pop on this page. All right, push num n pushes the non-negative integer value n. All right. Let's click on here. So push num 23. All right, so you're going to push 23 onto here. The stack grows downwards. So the bottom of the stack is here, and the top of the stack is here. Push num 23 will put 23 above this. So before, it's like this. After, you have 23 at the top of the stack, right? Let's look at this again. Push num. Okay, before and after. All right. So push stat add. That's similar to push num, but it pushes a pointer to a data memory location. So push stat add is here. Push stat add A pushes a pointer to the data memory location whose address is A. All right. So let's look at a picture. Push stat add 17. So that's going to push a pointer to this location. Right? So before, it's like this. After, we have this. Right? After execution of push stat add 17, you have a pointer to this location on top of the expression evaluation stack. And save to address. Right? Save to address. So it first pops a value v, then it pops a pointer p, and then it stores v in the memory location that p points to. Right? Pops a value, pops a pointer, then stores the popped value into the location that the pointer points to. All right, let's look at a picture. So suppose on top of the stack you have this value, 82,735. And below that on the stack, you have this pointer 247. Save to address, pop those two things, and store this number into this location. So, before, after. All right, let's see that again. Before, after. Right? So then, before, after. All right, so that's save to address. So now we're ready to do some translation. So what TinyJ virtual machine code will the TinyJ compiler generate for this statement? Now let's see where that statement is. That's this statement here. It's actually a declaration. It's really not a statement. Did I call it a statement? Well, well, there's an initialization there. All right. So now we need to look at the code generation rules. So the first two code generation rules will be needed to answer that question. First of all, the generated code. So by the way, this page is the page after. So this is the program we're translating. Then the code generated is on the next page. And after that, we have the code generation rules. So rules number 1 and 2. Rule number 1. The generated code begins with instructions that initialize each static int and static array reference variable that has an explicit initializer. The only types that are variables in TinyJ are int and array reference variables. There are scanner variables, but they're not genuine variables, as I mentioned last time. Okay. So if you've got a static int or if you've got a static int or static array reference variable that has an explicit initializer, then instructions have to be generated to actually initialize the variable. So in particular, you need to generate instructions that store 10 into the static variable y. Now, what if a variable has no initializer? So if a variable does not have an explicit initializer, no initialization code is generated, right? Now, you should know that in Java, static variables are initialized, right? So static int would be initialized to 0. In fact, a static object reference variable would be initialized to null, right? A static real would also be initialized to a static floating point number, rather, would be initialized to 0 as well, a floating point 0. And so static variables are certainly initialized in Java, and TinyJ is a subset of Java. So therefore, looking at this program, you should know that x is going to be initialized to 0 because it's a static variable. So like the variable x in, if this was a Java program, then x would be initialized to 0. TinyJ is a subset of Java, so therefore x must be initialized to 0. But yet, I'm saying here that no initialization code is generated. So how, you should be asking, does x get initialized to 0 if no initialization code is generated? Well, the answer is actually quite simple. The answer is that when the TinyJ virtual machine starts up, before anything is executed, all data memory locations allocated to static variables contain 0. And the null pointer is represented by 0. So if you've got an array reference variable, then it will be initialized to null without any code having to be executed. Right? No instructions have to be generated because when the machine starts up, the data memory locations allocated to static variables will all contain a 0. And so the initialization is sort of automatically happens. Okay, so now let's look at what should be generated here. So first of all, I want to make sure everybody still remembers x gets address 0 and y gets address 1. All right, this is from the this rule here, right? Nth static variable gets address n minus 1. So x is allocated address 0, y is allocated address 1. So we don't need to generate any instructions for initializing x. X will automatically contain 0 when execution begins, but we do need instructions to put 10 into y. So first we push a pointer to y. So push stat add 1 to push a pointer to y. So push stat add 1 pushes pointer to y. Blue means that after executing this instruction, this blue thing will be on top of the stack. Now we need to push 10, right? The 10 here. Push num 10 then. So now on top of the stack we have 10, and below that we have pointer to y. Now we need to save the 10 into y. So save to address, right? That will pop 10, pop the pointer to y, and store 10 into y's location. So these three instructions at addresses 0, 1, and 2 will execute this y equals 10. So we've answered this question. And if you actually look on this page, you can see that these are exactly the instructions that are generated and placed into code memory addresses 0, 1, and 2. All right, moving on. Just write a note to myself here. Right. Now, what is the first virtual machine instruction generated for each of the methods main, f, and g? Right. The first instruction generated for main, the first instruction generated for f, and the first instruction generated for g. So what are those instructions? And so let's look at the code generation rules. Well, let's get this rule out of the way first. Method bodies are translated in the order in which they appear. So what that means is that the body of main is translated first, then the body of f, and then the body of g. And this is really the simplest possible order. I mean, the compiler just reads the file from beginning to end, and it sees a method, it translates it. It's a method that translates it. And you can actually see the code generated. So here we have the code generated to main, because main is the first method. Then after the end of the code generated to main, we have the code generated to f. And then after that, we have the code generated to G. So method bodies are translated in the order in which they appear in the source program. All right, main, then F, then G. And that is the same order as you see in the source program. Main, then F, and then G. All right. Now the next rule, the code generated for each method, including main, starts with init stack frame, total number of stack frame locations needed for local variables declared in the method's body. All right, so let's look at a concrete example. So for this method, the first instruction would be init stack frame, the number of locations needed for these local variables A through K. Now, we worked out how many local variables would be needed for A through K last time. The answer was 6, I believe, right? Let's see. So it says 11 here, but you've got to bear in mind that 3 of 11 are used for the formal parameter, so that gets you down to 8. And I also said the 2 locations are used to support method call and return, right? That's the location 0 and -1. So 11 minus 3 is 8, minus 2 is 6. So I was right. The answer is 6. So it would be init stack frame 6, because you need 6 locations for these variables, right? So we just take a look. Right, you can see the answer is certainly 6, right? Because locations 1 through 6 here, +1 through +6, are the locations in the stack frame allocated to all these local variables declared in the body. All right, so init stack frame 6, because you need 6 locations for all those local variables. So going back to this particular example, how main's code begins with init stack frame. Well, let's see how many locations are used for local variables in main's body? 0, because there are no local variables declared in main's body, right? So init stack frame 0 for main. Now, what about for F? Well, you would need +1 for V, +2 for W, and +3 for U. So 3 locations are allocated for the local variables V, W, and U in the stack frame of F. So for F, the first instruction is init stack frame 3. For G, there is just 1 local variable, right? So only 1 stack frame location is needed for local variables declared in G's body. So the code G begins with init stack frame 1, right? So for this one, init stack frame 0, init stack frame 3, init stack frame 1, and we did a more difficult example last time. For this one, init stack frame 6, all right? Because 6 locations are needed for the local variables declared in the body of this method. All right. All right, so again, this is code generation rule number 4. So main stack frame has no locations for local variables declared in main's body, right? Because there are no such local variables. And the 3 local variables declared in X body are given 3 different locations, right? And the only local variable declared in G body is given 1 location. So now we have the answer. Right? Main's code begins with init stack frame 0. And F's code begins with init stack frame 3. And G's code begins with init stack frame 1. Now we know that for main, the code memory address of the instruction is 3, because we already saw that 0, 1, and 2 are used for instructions that perform this initialization here. So Main's code begins with 3 in its stack frame 0. Now, you don't know what code memory address this instruction, the first instruction of F, will be stored in. And that's because the answer to that question depends on how many instructions are generated for main. So the first instruction for F will be put into code memory at the address after the last instruction for main. All right? So you can't tell what it actually is. Colon omitted. What colon? No, the colon is just the format for how you write a 3 means the address, right? So it's not really the notation is unimportant, right? The important thing is that this is placed at address 3, all right? So you can write it with a colon or a comma, or it doesn't really matter. This is not a formal notation. I'm just trying to tell you what the address is. So you can put a comma, you can put a colon, 3 colons, or whatever you like, as long as it's quite clear that you know what the address is. Whereas here, we don't know what the address is, all right? So that's the important part, right? Whether there's a colon there or not, it's just that if I feel like putting a colon there, I'll put a colon there. So that doesn't actually make any difference. So the code memory, this is not meant to be machine readable. You see, that's the important thing. This is just meant to be human readable by you and by me. A code memory address is not known until main has been translated, right? And here, code memory address is not known until main and F have been translated. Okay. So, but what are the actual answers? So after you've translated them, then you will know, all right? So in the case where it's actually 34 in its stack frame 3 for F, and it's 60 in its stack frame 1 for G. So that's the answer. But there's no way you can know this until you've actually translated main, then you know this is 34. But until that time, you don't. And until you've also translated F, you can't know that this number is 60. All right, so what are the last virtual machine instructions generated by the TinyJ compiler for F and G? All right, so more code generation rules have to be looked at. Main's code ends with stop, and the code generated for each void method other than main ends with return K, where K is the number of formal parameters the method has. See, the difference is, in the case of main, when you finished executing main's code, you've executed the entire program. And so you should stop the machine. It's appropriate to stop the machine. So main's code ends with stop, because once this is executed, the machine stops. Whereas with other methods, when you finished executing the code for the method, you return control to the core. So therefore, you want a return instruction. Now, what is the K? The K is not the value that is returned. In fact, it can't be, because it's a void method, so it doesn't return anything. So the K is the number of formal parameters the method has. The K is there to tell the machine how many stack frame locations that were allocated to formal parameters have to be deallocated. So when you return control from a method, all the locations allocated for the stack frame of the called method have to be deallocated. And that includes the locations allocated to the formal parameters. So this instruction just says there are K locations allocated to formal parameters that should be deallocated. So K is the number of formal parameters. All right, so in the case of main, the code ends with stop. In the case of F, obviously, return 3, because there are 3 formal parameters. And in the case of G, obviously, return 2, because there are 2 formal parameters. Right? So from code generation rules 5 and 6, main's code ends with stop, and G's code ends with return 2. Now let's look at 2 new instructions. So write string Now, what is this instruction? Write string A primed. So this instruction takes as operands two data memory addresses. The instruction assumes the data memory locations whose addresses are between A and A primed inclusive contain the characters of a string literal. And the instruction writes the string literal to the screen. So it has to go through an implicit loop, looking at all the memory locations between A and A primed and writing out all those characters. So this is actually a powerful instruction. It does a lot of work. A hardware CPU would never have a single instruction that does as much work as this. If you were writing a compiler for a hardware CPU, what you would do is you would generate a call to a library function that does the same thing as this write string. But the library function would contain lots of machine instructions, not just a single instruction. But with a virtual machine, you can have a single instruction like this that actually does a lot of work. Okay? So that instruction does all this work. All right, so let's look at a picture. So write string 39. Well, let's suppose addresses 3 through 9 contain these 7 characters, the space cat. Now, when you execute this, the memory doesn't change. So you see that the memory is still the same. But what happens is the string the cat is written out, right? So the contents of the memory will not be affected. The only thing that will happen is these characters are written out to the screen. Okay. Next instruction, read int. All right, let's take a look here what it says. So read int assumes that the character sequence of an int will be entered on the keyboard. It reads that character sequence, which should be a sequence of digits, and computes the int value it represents. And it pushes that integer value. For example, if the sequence of digits 6, 2, 6 are typed at the keyboard, then 626 will be computed from the digits 6, 2, and 6, and that integer 626 will be pushed onto the expression evaluation stack. Again, this is a very powerful instruction. It's a lot of work. And the hardware CPU would never have a single instruction that does this much work. So again, a compiler for a hardware CPU would generate a call to a library function, and the library function contain lots of instructions which, when executed, will do what readint does. But for a virtual machine, it's entirely reasonable to have a single instruction that does all this work. And that's what the TinyJ virtual machine has. It's got this single instruction readint that does a lot of work here. All right, so readint. So read an integer from the keyboard and push its value onto the stack. So before, now, after. All right? Before, after. So now we know about these two instructions, we can do more translation. So what code would the compiler generate for the first two statements of the main method? All right, so these are the two statements, but let's take a look. So we're talking about the brown statement here and the green statement here. So what instructions are generated for the brown statement and the green statement? So first of all, we have to do a write string. But write string what? You see, what addresses are given to E to this string? All right. Now we did an example like this last time, right? You'll remember we did this example, right? So where I would enter X and in F be placed, and so we did this example, and so we saw the answer. So what we are using is this rule, string up this rule here, all right? Okay, so X is given address 0, Y is given address 1, so E gets 2, N gets 3, T gets 4, E gets 5, R gets 6, 7, 8, 9, 10, 11, 12. So 2 through 12 would be allocated to this string. All right, so there we have the answer. So X is allocated 0, Y is allocated 1, and the 11 characters in here would be given 2 through 12. So for this, we need right string to 12. Right, so for 4, here, right string to 12. Right. Now, what about for this? Well, this is an assignment. So like the other assignment that we did a long time, a while ago, y equals 10, we're going to first push a pointer to the variable, to the target variable, then the right side onto the stack, and then save to address. All right. So first, the pointer x. Well, x is given address 0, so push stat add 0 is what we want for at address 5, pushing pointer to x. Now we want to read something from the keyboard and put its value on the stack. So read it is exactly what we want. Right? And now we have the value of the integer that's been read on top of the stack, and below that we have a pointer to x. So save to address will save this value into x. Save to address, right? Pops the integer, pops the pointer to x, then stores the integer that's been read into x's location. All right, so what we've just done is we're translating the brown and the green, and so we've just written down these 4 instructions, the brown instruction and the 3 green instructions there. Okay, moving on. Now we're going to look at some more instructions. Push local address. Now this is rather like push static address, but where push static address pushes a pointer to a particular data memory location with address A, push local address pushes a pointer to the data memory location at offset S. Right? Offset S. It says my connection is poor. Oh, well, at least that has gone away. So it pushes a pointer to the location of offset S in the currently executing method activations stack frame. All right, pushes a pointer to the data memory location of offset S in the currently executing method activation stack frame. So let's take a look. So let's suppose this is the current executing method activation stack frame. That will actually be on top of the stack of stack frames. I just want to remind you of this. Remember this exercise we did right at the end of the last class. So when you call a method, its stack frame is pushed into the stack dynamically allocated part of data memory. So main calls F, F stack frame is pushed. F calls G, G stack frame is pushed. Every time you call a method, its stack frame is pushed, right? If F returns control to G, then F stack frame is popped. So the currently executing method activations stack frame is going to be right on top of the stack dynamically. Is going to be in data memory at the top of the stack of stack frames. But remember, this is a part of data memory. So this is somewhere in here, right? It's not important exactly where, but you need to know that this is somewhere in data memory, all right? So data memory has 3 parts. There is the stack dynamically allocated part, statically allocated part, the stack dynamically allocated part, the heap dynamically allocated part. All 3 of these together constitute data memory. All right, so this stack frame is somewhere in here. So push local address 3 pushes a pointer to here, pushes a single pointer. Now watch it push a single pointer. Now these 2 are the same pointer, right? The 2 arrows represent the very same pointer. What this picture is saying is that this location is the same as this location. So I told you that this stack frame is somewhere in here, and so this picture is saying that this location is actually this location. So again, before, after, right? Before, after, push 1 pointer onto the stack. The pointer points to the location at offset 3 in the currently executing method activations stack frame. Load from address is used to dereference a pointer. Load from address pops a pointer P, and it pushes the value that is stored in the memory location P points to. Another way of thinking of that is that it replaces a pointer that is at the top of the stack